So it's a pleasure to be here to talk about something that's interested me for a long time, which is life in the universe. And tonight I want to talk about the most exotic end of life in the universe, which would be whether there are any other intelligent creatures out there capable of building a technological civilization comparable to our own, or conceivably more advanced than our own. And searching for such a thing goes by the name of SETI. This is an acronym, the Search for Extraterrestrial Intelligence. And SETI is pursued by a small subset of astronomers who search the skies looking for evidence of extraterrestrial artifacts or extraterrestrial signals, and most of it's been conducted by astronomers searching for radio waves of artificial but extraterrestrial origin. And SETI started in 1960. That was the first attempt to search for artificial radio waves, and it's been so for 56 years now. SETI has been searching, and currently it's found nothing. So the question is, or a question is, whether we should be surprised that SETI hasn't found anything. And so at this point I need to introduce my one prop for this evening, which is written here, but I've got some handouts, so I shall hand them round. The first, oh, you're going to hand them round. Well, I'll hang on to one of them, thank you. So the first astronomer to start searching for alien signals was an American radio astronomer called Frank Drake. And in 1961, so one year after he conducted the first radio search, he decided, and he found nothing, of course, because none have been ever found since. He decided to try and estimate whether it was all a waste of time, whether he would expect to see. It's possible some people at the back, even on this side, might benefit from a handout because it's really small. So thanks. And so he produced this equation, which is now named after him. It's called the Drake equation. And the Drake equation is an attempt to try and estimate how many of these technological civilizations there might exist in the Milky Way galaxy. So for those of you who don't like equations, this may look scary, but actually it's a very simple equation. All of these letters just stand for things that we don't know, multiplied together. So it's just 1, 2, 3, 4, 5, 6, 7 numbers multiplied together. And Drake, and I'll explain what they are in a minute, obviously, but Drake did this because he thought that n at the front is the number of technological civilizations present in the galaxy at the moment who in principle might be communicating or in a position to communicate with us by radio waves. So Drake was a radio astronomer, so his definition of intelligence, well, almost, but not quite, to be fair to the man, was because he has introduced a separate term, but almost, it's kind of intelligent life is life which builds radio telescopes, but not quite. It's not quite as stark as that. Anyway, so what he wanted to know was whether n is big or small. And so he thought about this and decided it could be broken down into the number of stars and then the fraction of stars with planets and the fraction of planets on which life evolves and whatnot. And that's more or less what this equation is. But I'm just going to go through it. First of all, I'm going to define the terms for you. And then I'm going to explain the rationale for this equation, and then I will tell you what we think we know the various numbers are. So there are 1, 2, 3, 4, 5, 6, 7 terms in this equation, and it starts with r subscript star. And r subscript star is the rate at which stars form in the galaxy. Now, this is one of the few things that we think we do know. Star formation rate in the Milky Way galaxy is about 1 per year. It might be a little bit more. I mean, it might be 4 or something per year, but it's of the order of a star per year forms in this galaxy. Then he's multiplied it by little n subscript e. Oh, sorry, no, I've missed something. I've missed something important out here. Oh, do I have a pen? So, in trying to get this onto the sheet of paper, I have to make a very important change here. An extra term. There's an f subscript p goes between the r star and the n. So those of you who can see what I'm doing, there's one of these f's, and one of these F's with a subscript P in front of it. Sorry about that. And this is the fraction of stars that have planets. So if one star in the galaxy forms every year, if a fraction 1, 100% of stars have planets, that would be the fraction at which stars with planetary that would be the fraction of planetary systems that form every well, it'd be the number of planetary systems that form every year, because you multiplied it by the number of stars that form per year. But of course, we don't know that all stars have planets, and certainly, I think actually now we've got a very good idea that we do know that most stars have planets. But when Drake wrote this equation in 1960, this was one of the big unknowns. Do all stars have planets or not? So F subscript P, quite important. Then he's multiplied the n subscript e is the number of planets. Little e stands for environment, because even if you've got planets, it doesn't follow that all your planets have an environment suitable for life to evolve upon. And so in our solar system, I mean, n is at least 1 because life has clearly evolved on the Earth. But Mars might be habitable, Jupiter's moon Europa might be habitable. In principle, there might be a number of habitable planets in each planetary system. So n might actually be bigger than 1, but it's at least 1 in our solar system. And so that would be, having multiplied the rate of star formation by the fraction of stars with planets and the number of habitable planets per planetary system, that's the number with which number of habitable planets that form in the galaxy every year. Then he's multiplied it by these 3 things. So these little squiggles are just F's, right? F stands for fraction, that's all. And F subscript L is the fraction of planets on which a life evolves or arises from non-life. We don't know what that is, of course. And then F subscript I is the fraction of such life that goes on to evolve to be intelligent. We don't know what that is either, of course. F subscript C is the fraction of this intelligent life that will go on to build radio telescopes. So C here stands for communicative, because to a radio astronomer, you're communicative if you build radio telescopes as your means of signalling across interstellar space. Now, and then multiply right at the end is capital L, and capital L is the lifetime of a communicative civilization, and we don't know what that is either. So first thing, 2 things. First of all, this equation sums up a lot of ignorance, right? In a way, our ignorance increases from left to right, in that the astronomers are confident, more or less, that we know the rate at which the rate at which stars form. We now know, thanks to astronomy, that's been one of the most exciting things in astronomy over the last 15 years has been the discovery of planets around other stars. And the statistics are now such that we can say that actually most stars do have planets. Now that's real progress, so Drake didn't know that 50 years ago. We know now that most stars have planets. Whatever process as stars form out of gas clouds, this process of forming stars seems to automatically make planets. So actually, we do know that our star is of order 1 per year, and the fraction of stars with planets is about 1 as well. The number of habitable planets in a planetary system, we don't know that, but it's a few, arguably, in our solar system. So one would not be an unrealistic estimate. So we've got 1 times 1 times 1, so this equation is looking quite simple so far. But then all of these fractions, the fractions of planets on which life evolves, the fraction of life that evolves intelligence, etc., we don't know these at all. So these are the real unknowns in the Drake equation, and neither do we know the lifetime of a technological civilization. So from about the middle of the equation onwards, we're really quite ignorant. But we might have some guesses, which is what I'll come to in a minute. But the other thing I want to say about this equation, I just need to, just in case it isn't clear, if you take the rate at which stars form in the galaxy, and multiply them by the fraction that have planets, the number of those planets that are habitable in principle, so that might be planets with liquid water, say, times the fraction of those habitable planets on which life actually evolves, times the fraction of that life that becomes intelligent, times the fraction of that intelligent life that can build radio telescopes, you've got here the number of communicative civilizations that appear in the Milky Way galaxy every year. and it's every year because you started off with the rate at which stars form per year at the beginning. And then if you want to know how many there are in the galaxy at the present time, a bit of sleight of hand here, because Drake is an optimist and he believes, and still believes, because he's still alive and still quite active, that intelligent civilizations are common in the galaxy. If you think you're dealing with quite large numbers here, then statistically, if you take the rate of formation, if you want to know how, if you've got some, you want to know what is the equilibrium population of something, whether it's civilizations or people or anything, if you take the rate at which they form and multiply that rate formation by the average lifetime, you've got the equilibrium number that exists at any one time. So he's got the rate at which civilizations form. If you multiply that by the lifetime of a civilization, that will be the number that exists at any given time. That is that is the thinking behind the Drake equation. Does anyone have any questions so far?
So is there perhaps an assumption that we're already at equilibrium? There is some delay.
Oh, well, yes, so I might come to that. And actually, if you're dealing with small numbers, it breaks down anyway. So actually, there is a sleight of hand in the Drake equation. He's already kind of assumed that extraterrestrial civilizations must be really common in order to get away with this formulation. And I might come back to that.
So what is radio waves? Do you consider the other waves?
Oh, so the SETI people these days, I mean, I'm not one. I mean, I have to teach this in my astrobiology class at Birkbeck, but I'm not a SETI researcher. So historically, radio waves were, well, there was a certain logic. Human civilization emits a lot of radio waves, maybe others will too. And then practicality, radio astronomy after the Second World War, radio astronomers started building these big radio telescopes, so it became kind of logical that you... But of course you're right, it's a bit of an assumption. So we use radio waves, maybe they might use something else. So SETI has in the last decade or so, they've started looking for optical signals. These would be lasers. They'd be aliens trying to send Morse code to us with laser beams instead of radio waves. So I think the community, and they haven't found any of those either, but the community is aware that, you know, the radio assumption is an assumption, and so ideally you consider other things. Shall I take another question on this equation first, because I'm going to go through the parameters, but everyone's happy with or at least understands. I mean, we don't have to be happy, because I've already said there is perhaps a fundamental flaw in the way Drake did it, but this is the Drake equation. And if you Google it, of course, there's a big Wikipedia article on the Drake equation, as you might expect. So, but anyway, the fact is we haven't discovered any aliens yet. So should we be surprised? And that depends on what we think numbers are for these fractions towards the end of the equation. So if you're an optimist, like Frank Drake is, where optimist means you think there's lots of alien civilizations in the galaxy, you will argue as follows. Given a habitable environment, which you've already included, life will automatically evolve is the wrong word, because once you've got life, it can start to evolve. Life will automatically arise in a habitable environment. Now, that we don't have to agree with that, because a pessimist would argue differently. But if you were an optimist, and we don't know how life arises from non-life, right? It's one of the big unknowns in biology. The one piece of evidence you might appeal to, if you wanted to be an optimist, was it is true that if you look at the fossil record of life on Earth, life was present on this planet almost as soon. I mean, the planet is 4,500 million years old. And the oldest evidence we've got for fossilized microorganisms, of course, because that's all we've got for these very early times, is about 3.5 to 3.8 billion years. So you could argue that life appeared on this planet very quickly after the planet became habitable. You might argue that although we don't know how life evolves from non-life, nature knows how to do it, and it happens quickly in suitable environments, which will be planets with liquid water, probably carbon dioxide atmospheres, a lot of volcanic rock, etc. Because we don't know that, but if you were an optimist, you'd assume that. But anyway, if you're an optimist, you'd put all of these fractions to be 1. Because having decided that life will inevitably arise on suitable environments, you would then argue that natural selection is a very powerful means of driving complexity in living systems, and intelligence will always have evolutionary survival advantage. So it will always be selected for by natural selection. So given life, intelligent life is well, likely, or take it to an extreme, inevitable. And then F subscript I would be 1. And then if you argue that that given intelligent life, you will always eventually discover electricity and radio waves and whatnot, you will build radio telescopes, and at some point therefore some intelligent life will inevitably be able to build radio telescopes, then the fraction of this intelligent life that becomes communicative will be 1 as well. So if we take the star formation rate to be 1, which it sort of is about, but it might be a bit bigger. But anyway, let's take it to 1. You've got a really simple, per year, you've got a really simple equation. N equals 1 times 1 times 1 times 1 times 1 times 1 times L. And L is the average lifetime of a technological civilization, and we don't know that because that's into the realms of extraterrestrial politics and extraterrestrial sociology, and we don't know. But the most optimistic possible solution to the Drake equation is everything is 1 before L. So then you'd have that N equals L. And since you've done this R star is in stars forming per year, L would have to be measured in years. And so Drake, for a while, was so taken by this, he actually had a personalised number plate that made for himself that he drove around his car in California in, and it said N equals L for those who might know, right, for the initiated, right. And that was before Wikipedia, of course, so no one could look it up. But N equals L is the most optimistic possible solution to the Drake equation, because all of these fractions are 1. Of course, we don't know what L is. So Drake, and indeed SETI optimists like Drake and Carl Sagan and others, kind of like, I mean, there's no particular justification, but they kind of like a number of 1,000 years. They like to argue that technological civilizations, once they've evolved, will have an average lifetime, it's an average of course because we're dealing with large numbers, of about 1,000 years. Now, firstly, they like this because it seems plausible. It's comparable with the history of civilizations on this planet, although of course we haven't been a technological civilization in this sense for more than 100 years yet. But it's not absolutely outrageous. It's not like they're claiming civilizations might live for thousands of millions of years or anything like that. The second thing they like it, the second reason they like it is not only does it seem plausible, it gives an answer that they're comfortable with, because then it would mean N equals 1 times 1 times 1 times 1 times 1 times 1,000. It means there'd be 1,000 technological civilizations in the galaxy today. Now that seems a lot, and it would be quite exciting to consider that there might be 1,000 other civilizations out there. But it means they don't have to be kept awake at night realizing they haven't detected any of them yet. Because the galaxy is a big place, and if there are 1,000 civilizations in the galaxy today, the nearest one will likely be of the order of 1,000 light years away. This is a long way, and it's actually beyond the distance of the current SETI search's sensitivity. So they can, if you believe L equals 1,000 years, you can be an optimist in the sense that everything's 1. If L's about 1,000 years, you've got a galaxy with a good number of civilizations in it, but you don't have to worry that you haven't detected it yet, right? The negative SETI research searches are not a failure. And indeed, it's kind of on the cusp. You can be motivated by this because you might get out of bed tomorrow and go to your telescope and find that it's found something, right? You might hope to have detect something within the lifetime of current searches. But that's the most optimistic solution. So immediately you can see actually the fact that SETI's not found any alien signals yet certainly doesn't tell us that there are none out there. There could be up to 1,000. On the other hand, there could be a lot less because some of these fractions might be a lot less. We don't know how life appears from non-life. It's like I said, it's one of the big mysteries in biology. It might not at all be inevitable given planets with liquid water and carbon dioxide, atmospheres and volcanism and all the rest of it. It might be really, really unlikely. And so this fraction could be a lot less than 1. And similarly, once you've got life, doesn't actually follow that intelligence is inevitable. It did take, I mean, there's been life on this planet for at least 3,500 million years. Intelligent life in Drake's definition appeared about 100 years ago. So it takes a long, well, actually, strictly speaking, that would be his communicative life, right? But intelligent life was still of that order, perhaps a few million years ago. So it's taken most of the history of the planet to evolve intelligent life, and that might imply actually it's really hard. And this fraction, even given life, the probability of it ever evolving intelligence might be really low. And of course, even intelligent life, it doesn't follow that all intelligent life will inevitably produce radio telescopes. I mean, you can imagine there are dolphins, there are octopuses, you can imagine equivalents out there which it might be very intelligent animals, but either have no ability to build radio telescopes or no wish to build radio telescopes, right? So this number could also be small. In which case, of course, even if the lifetime's 1,000 years, you're going to have much fewer than 1,000 years, much fewer than 1,000 technological civilizations in the galaxy at any one time. Now, and just before you have your sort of break, am I close to break time? But I just want to leave you with a thought, right? Because lots of people have pored over this equation, but I think one of the biggest insights came from someone who was considering this question long before SETI and radio astronomy. There's an evolutionary biologist by the name of Alfred Russel Wallace. Can I just ask, who has heard of Alfred Russel Wallace? Okay, that's good. I mean, Alfred Russel Wallace is one of my great intellectual heroes, but of course history has sort of passed him by because he's totally obscured by Charles Darwin. Alfred Russel Wallace was the co-discoverer of the principle of natural selection with Darwin, and he arrived at it completely independently while he was collecting insects in what is now Indonesia. And he had this idea in 1858. Essentially, he had this idea how species might evolve, and he wrote to Darwin, who was famous, of course, and basically said, Darwin, I've had this great idea, and the great idea was basically natural selection. And it was when this sort of letter appeared on his doormat that Darwin realised, actually, other people are starting to think about this now, and I've been sitting on the theory of natural selection for 30 years, and I'd better get it published. And so he had about a year, basically, a quick writing to get the origin of species out. So really, the principle of natural selection was sort of co-discovered by Wallace and Darwin. But Wallace was very interested in these subjects. And in 1903, Wallace wrote what is probably the first astrobiology book. It's not really a textbook, but an astrobiology book, Life in the Universe. It was called Man's Place in the Universe. And it was published in 1903. And he started to think that in the context of evolutionary biology, actually it might be really hard getting from life to intelligence. And because he realized that evolution's got a lot of hoops to go through, and a lot of the things that you may have had to go through from the origin of life to intelligent life might have very low probabilities of occurring, and some of them might just have been chance. And we might have been really lucky in our own history. And then if you multiply all of these things together, and they're all low probability, the total probability of evolving intelligence from microbes might be really low. And two interesting things about this. First is that here was right at the very beginning of evolutionary biology, by one of the two discoverers of the principle of natural selection. Wallace was already applying it to life in the universe. That's quite interesting. And the other is the number he came up with. He didn't know how unlikely it might be to evolve intelligence from life, which basically might be essentially evolving from things like bacteria, essentially, to things like you and me. But he thought it might be difficult, and he plucked a number out of his head. He had no justification for it at all, really, but he thought the probability might be really low. The probability his number was, might be a probability of 1 in 100 million. Now, there's no particular justification for that, except he thinks the probability is low. But if you were to take his number, it means f subscript I, the fraction of life that evolves intelligence in this equation, instead of being 1, which is the optimist number, would be 1 in 100 million. It would be 10 to the power of minus 14. Now, if you stick that in the equation, it sinks it. obviously, even if everything else is 1. And they might not be. I mean, many of these other numbers might be smaller than 1, of course. But even if you just take everything to be 1, even except the fraction of biologies which evolve intelligence from simple microbes, if you took that to be 10 to the power of minus 14, you've got 1 times 1 times 1 times 1 times 10 to the power of minus 14 times 1 times whatever you think L is. If you stick the same 1,000 years in here, you've got 10 to the power of minus 14 times by 1,000, that's 10 to the minus 11. So then you're expecting 10 to the power of minus 11 civilizations in the galaxy today. So what does that mean? Well, how can you have 10 to the minus 11th of a civilization? Well, the answer is you might expect to find one such civilization if you looked in 10 to the power of 11, that's 100,000 million galaxies. Well, there are about 100,000 million galaxies in the observable universe. So we would be it, right? We wouldn't just be the only intelligent civilization in the Milky Way galaxy, we'd be the only technical civilization in the entire universe. If Wallace's number for the fraction of the probability of evolving intelligent life from life is at all in the right ballpark. So you've got these two before you have your tea break, and I attempt to answer any questions, or beer break. You can see that we've got a very optimistic solution. There might be 1,000 civilizations in the galaxy today, to a very pessimistic one where there might not only be none in the galaxy, we might be the only example in the entire universe. And we can't pin this down because we don't know what these fractions are. Right? We don't know whether Wallace or Drake is closer, there, right? And so basically this is what drives astrobiology as a discipline. It's trying to explore the universe to see, in recent years we've pinned down the fraction of stars with planets. That's been progress. What we now need to do is start pinning down these fractions. How likely is it for life to evolve in suitable planets? And the good news is we've got a planet next door, right? Mars was Earth-like, and certainly was more Earth-like in the past planet with liquid water and whatnot. And so if F subscript L was about 1, you'd predict that life would have evolved on Mars, at least in the planet's early history, even if it's now extinct. So we can go to Mars and study Mars, and we might get some experimental, empirical evidence for what this fraction is. And similarly with the others. But until we can get out into the universe and explore it a bit more and start having more realistic values for these fractions, then basically we're not going to be in a position to know whether we should be expecting to get a signal from an extraterrestrial civilization or not, because we might be the only one. Okay, shall I leave it there?